Hello everyone. So the topic for my talk is using Blackbox ML techniques to diagnose QoE problems for an IPTV service. So this is a problem we have been working on for quite some time with my colleagues at Ericsson Research. So first, some brief introduction to the problem. So as we know that the IPTV services continue to disrupt the traditional cable-based TV delivery, and they continue to grow in popularity. But at the same time, of course, they face a lot of challenges related to the delivery of stable and problem-free video streams, while at the same time minimizing downtime. The main problem here is that the this IPTV service is actually delivered on the IP-based networks, and they are, as we know, they are best effort networks. And due to their inherent complexity and uncertainty, there is also uncertainty in the delivery of high-quality IPTV service. And this is the problem we are aiming to tackle with the ML-based technologies, to trying to detect the downtimes and also trying to find the root causes for the problem. So the main goals for us at the high level are first to develop and evaluate the machine learning models to predict the QoE problems in the centralized and distributed learning scenarios, trying to see the pros and cons of both approaches. Although in this paper we will be focusing only on the centralized techniques. Secondly, to develop the explainability models for the localization of the causes of the different QE problems. That's the core of the work that we will be presenting. And finally, to compare the two main approaches, the black box and the white box techniques for doing the root cause analysis. Yeah, and the second main step obviously is to develop an environment to implement and test these models in the operators network environment. This is something that we are doing also in parallel, but will not be discussed in this presentation. So this is how the network topology looks like. As you can see, we have the backbone network and the which is a mesh network in the consisting of different core routers in the different cities. This is connected to the aggregation switches, and they basically lead us to the different buildings and the home networks. And the different homes in the each building are connected, usually using the Wi-Fi network, to the building switch and then to the aggregation switches and so on. We collect data at the different points in this whole end-to-end network, from the backbone networks, also from the aggregation switches, the data from the Wi-Fi networks, and also from the STB boxes. And then the of course also the service data is collected, as we will see in the next slide. This is just to summarize and give you an overview of which kind of data we collect. As I said, there is the tabular data, which is the Wi-Fi data that we collect from the routers and the access points, very detailed data at a very high time resolution. It's collected usually at every second. For example, the RSSI, bandwidth stats, the different packet stats, and so on. Then there is the traffic data we collect from the core routers. It's usually the bandwidth usually coming in the in traffic and the out traffic from the routers, which is time stepped. So it's also time series data. And then we have the data that we collect from the switches, which is the in traffic and out traffic. And then also regarding the service, we have the data about the service current service state. So it could be service could be running fine, which is represented by this green OK variable, or it could have some minor issues. Or the third state is like it could have some major problems, or simply the service could be unavailable. This thing is reflected by this kind of four states in the QoE data. So this basically, for our machine learning model, this works as the labels, and this is something that we are trying to forecast in the future. We also have data from the STB device logs, which is text-based data, and also the customer calls tickets, which we are working to correlate with the tabular data, but for the scope of this study, this will not be discussed here. So just to give a quick overview of the ML problem. So basically we are trying to predict the gamma OK variable. So it's a binary classification problem, and so what we would like to predict is if the service is running OK or it's not running OK. So if the service is predicted to be running smoothly, if and only if the OK state is expected to be greater than 99%. And of course, we already discussed the input features from the backbone routers, switches, and the Wi-Fi data. So as I said, it's a binary classification problem, and we aim to forecast the KPI for the next time step ahead of time in the next time step, using the data from the previous time steps that they have, so that we can, if there is something is going to break, then we can do something proactively. And lastly, we of course would like to do some kind of cause inference and the root cause analysis. So we will be discussing two types of algorithms. The one is the classifier type algorithms, random forest, very popular algorithm, XGB and MLP. And they are the special type of explainer models, which we use for the explainability aspects. And we have the Blackbox method like LIME and SHAP, and for the Whitebox we use the feature importance from the XGB model. Just to give you the basic concept of the black box and the white box, we can see for the white box methods we have the conceptually it looks like this. We have data, then we have trained white box model, and the same model can be used for doing the predictions and also to explain the model. In the black box, again we have the data, and then we assume that our model, our trained prediction model is black box, and it's only used for predictions. But then this model and the data can be input a special type of model, which is we call it like the black box causeinference model, or it's simply actually an explainer model, and this gives us the explanation. So we can see that the for the as compared to the white box, we have the specialized model for doing the explainability. Just have a super quick introduction to the LIME and the SHAP before we go to the actual discussion about the different results we got for the black box and the white box techniques. So the LIME is actually a method which generates the human readable interpretable rules that drive the model prediction. It's a black box technique, and it can be in principle applied to any prediction model to get the insights on how the model is driving its predictions. At the high level, it works like this. We basically take in as input the original model, the current sample, and the current sample prediction. And then based on the current sample, we basically generate a set of perturbations, and these synthetic set of examples are generated. So they are then input to the Blackbox model to generate the predictions. In this way, basically what we have is like some kind of artificially generated data set that can be used to train now a linear model, which is much more interpretable. So for example, the linear regression model. And then then we can generate the examples that are weighted based on the distance from the original example when used for training in the white box. The thing with the LIME is that it's pretty accurate, at least in the local context. When we are trying to use it for the local explainability, it's pretty good in most cases. Another advantage is obviously that LIME has a very fast computation, can be used for large data sets also. So Shapley is another technique. Shapley values is another technique which has been very popular recently. It's actually, the concept is not very new. It has been originally derived by the Lloyd Shapley in the 1950. But it has been only recently that we have some efficient methods to compute the Shapley values for the different type of machine learning methods. For example, the tree-based, there's a new very fast computation method for tree-based methods, and we can also do it for the other methods like neural networks and so on. So the main thing is that Shapley is basically a measure of the feature variable contribution toward the prediction of the model output when a feature is introduced into the model. So it gives the reflection on the how important a feature is, how much it's contributing to the predictions that a model is making for a specific sample. So it can do the local explainability. And the main design objectives are the consistency, accuracy, and the uniqueness. You can read more about them in the paper. There are different variants, and for example, there are dedicated SHAP methods for the trees, which are very fast and they provide the exact solution for the SHAP values for the trained prediction models. Then we have also the variants for the neural networks and also the more general kernel SHAP, which provide the approximate solution for the any arbitrary method, although it's much slower in computation. In this study, we will be focusing specifically on tree SHAP, mainly because this is the method which is the more practical and can provide, in some sense, the real-time SHAP values on a per sample basis. We found the deep SHAP and the kernel SHAP to be very, very slow in the computation. So the SHAP basically uses some kind of, as they call it, the force plot to reflect on how the different features are contributing towards making a specific prediction. So what you can see in this, for example, what you can see here is like if the base value or the nominal value for the class 1 prediction is like 0.18, then certain all the features in the input are kind of pulling this base value with a positive strength. For example, this blue color are the negative strength. So the positive strength, which is shown with the red color, and also or maybe with the negative strength as shown with the blue color here. So the base value in the end for the class probability ends up at 0.10. And you can see the different Shapley values actually shown at the bottom in this force plot. So the force plot basically gives us a kind of a method to reflect on the different SHAP values if we are interested only for the in the kind of explainability for a single example. Now looking into the Whitebox feature importance method, XGB is very popular machine learning method to use for the predictive analytics, and there are various ways how we can extract kind of feature importance from the XGB. For example, there are weight-based methods, cover-based methods, and there is the gain method, which is also called the Gini importance. And this is the Gini importance is the method that we will be using to extract the feature importance from the trained XGB model. The reason for this is that this has been shown to be much more robust as compared to the other two methods. And how it works is basically that this Gini importance basically shows that how much error is actually reduced on average in the model when a certain feature is used to split the input data on the tree branches in the model. So now coming to the results for our forecasting models, let's look at the three main competing predictive models. We have random forest, XGB, and MLP. And we can see that the results are the F1 scores and the precision recall are not really very good for any of the methods, but in the comparison, and the main reason is that that the data is very imbalanced. Like almost 95% of the data belongs to the class 0. So it's that's one reason. And secondly, that we found that the actual correlation between the input features in the access networks is not very strong with the service quality that we are trying to produce. So these basic two factors actually bring us challenges to do the predictions with the very high quality and to achieve the good F1 score. But nevertheless, we see that in this three methods, XGB provides the best performance in terms of the F1 score and also precision and recall. And still it can be used actually to get some good insights about the features that contribute towards the service up or the downtime. So first we look at the summary plots for the distribution of the input features, and this is basically shows the distribution of the SHAP values for the different input features. And here we use the XGB as the base model. We can see that the medium available is, and this is basically based on the test data, and it's basically a summary plot. And we can see that the medium available has the highest spread, and it's the most important feature if we consider from the SHAP value perspective. And also the channel variable is extremely important, and there are of course then there are some other features like bandwidth related features in the network. And some other observations are like we can see that if we have the high value for the feature, for example the medium available, which is shown by the red shades here, it contributes the negative SHAP values, which is to say that it's reducing the class 1 probability. So the higher values of medium available are actually helping us to kind of reduce the downtime for the service. So the service will be mostly okay when we are trying to increase the medium available values. The same can be said for the channels. If we select the higher channels for the our Wi-Fi network, then this contributes towards the negative values for the SHAP, and so in effect, basically, we are kind of increasing the or rather. This just shows that how these all three different approaches, the SHAP, XGB, and LIME, compare to each other. And we can see that they pretty much actually agree with each other on most of the variables, except that we can see that in LIME, the positions has switched for the top two channels, channel and the medium available. But when we actually talked about the top contributing factors toward the service downtime and uptime with our experts, and and they also verified that indeed the most of the channel, the Wi-Fi actually is one of the most important factors, which is actually contributing towards the service problems when there are issues, when the service is, for example, not running okay, then they are indeed the Wi-Fi is the main culprit actually there. In terms of conclusion, we can say that the gamma KPI is actually very challenging to predict due to the high class imbalance and less relevance. We have validated a solution, RCA-based solution using LIME and SHAP, and our experiment results show that SHAP is the most suitable approach for us diagnosing the IPTV QoE problem. Of course, the downside is that the SHAP requires some additional computation, and overhead is much larger as compared to the LIME. For the future, we are looking into the counterfactual generation, which is another promising technique which can be used for the model explainability, and this is something that we are currently working on. Thank you very much. If you have any questions, please put them in the chat box. I will try to answer them. Thank you.